Okay, so in this video, we're going to go over the thermodynamic principle that is Gibbs free energy. And Gibbs free energy is really the end all and be all of determining whether something is thermodynamically favorable or not. Gibbs, which is represented by the variable G, is determined by looking at the relationship and the interplay between enthalpy and entropy. Now, that's not to say that this is the only way to calculate delta G, because there are several applications of Gibbs. There is a particular Gibbs that we use with equilibrium. There's a particular Gibbs that we use with electrochemistry information, but this is the thermodynamic Gibbs, and that's the one that we're going to focus on in this particular recording. So, like I said, Gibbs ties together the enthalpy, the delta H, and the entropy, the delta S. So remember whether something is going to be endo or exothermic, and whether something is going to be increasing or decreasing in disorder as the reaction proceeds. So the equation that we're going to be using here is delta G is equal to delta H minus T delta S. And that T there is going to be the temperature. And so when we look at the equation, one thing to keep in mind is that if there is a change in temperature, it is going to be more appropriate to think about how it affects the T delta S term. And it's the T delta S term a lot of the times that we are going to be referring to as we talk about changes in temperature. You're going to hear me say the words, the magnitude of the T delta S term, because that's really important in determining what's happening overall with Gibbs. All right, so we know that delta H and delta S have two particular states each. They can each be positive or negative. And we see that the same thing occurs with Gibbs. So we're going to run through the different examples of the sign of each of these things. So first of all, with Gibbs, a negative delta G is the favorable condition. This is the thermodynamically favorable condition of Gibbs, meaning, even though I don't like to use the word spontaneous, that the reaction would be spontaneous. It is thermodynamically favorable. It is likely to occur without outside intervention. Then a positive delta G would be the opposite. This is unfavorable. This is non-spontaneous. This requires a significant input of external energy. The units for delta G are kilojoules per mole. Same thing that we saw with our delta H. All right, and then delta H we've already talked about. We know negative delta H means that the reaction is exothermic. A positive delta H means that our reaction is endothermic, kilojoules per mole again. The T here is obviously the temperature. What's important to know is that the temperature, when we are dealing with Gibbs, is got to be in Kelvin. So Kelvin temperature, to find Kelvin from a Celsius temperature, you take the Celsius temperature, you add 273 to it, and that'll give you the Kelvin temperature. The reason that we have to have the temperature in Kelvin has to do with the units for our entropy, delta S. So we know that a positive delta S means that the disorder is increasing, that the negative delta S means that the disorder is decreasing, and our units is joule per mole Kelvin. And so again, because the temperature is in Kelvin, we can cancel the temperature units off of the delta S, which is why the temperature is with delta S as opposed to being with delta H, because that's how we make the units work. All right. And so we should be able to understand what's happening with Gibbs, both with and without numerical data. Obviously, with numerical data, it's a plug and chug scenario. You plug in the H, you plug in the temperature, you plug in the S, it gives me a G. That G is either negative or positive. And I can use that value to make my statement of, well, this reaction is favorable or not. But without delta G, or without the numerical data, I should say, I have to really understand what's going on with the signs of these and algebraically what that tells me. So that's the first thing that we're going to look at, is general trends in Gibbs when I don't have numerical data. Now, before we get into this, remember that we said prior to this that if I don't have temperature data, the only thing I can do is assume that H and S are opposite. And if you actually break this down by row, I did it favorable variables on top, unfavorable variables on the bottom, that the favorable condition of H and S do have opposite signs, and the unfavorable has opposite signs. So if I don't know anything about temperature, all I can do is assume that H and S are opposite. If I have temperature information, now I need to consider how they actually play together to make G. Okay? So again, our general trend, we're going to be looking at the equation. Delta G is equal to delta H minus T delta S. And so let's look at our first scenario. My first scenario here has a negative H, delta H, and a positive delta S. And so we know that the negative H, exothermic, is my favorable H, and the positive S, disorder increasing, is my favorable S. And so having the two positive scenarios, I should end up with a favorable G as well. And so let's look at this mathematically. So delta G is equal to, I'm going to have a negative H minus the temperature, which is a positive Kelvin value, times a positive S. Okay, so let's look at what's happening here mathematically. So a positive S times a positive temperature is a positive number. So what I have here is a negative minus a positive. So that means that no matter how I slice this, delta G is going to be negative. In fact, at all temperatures, we're going to see that delta G is going to be negative. So therefore, if I have a negative H and a positive S, delta G is negative at all temperatures. Because it does not matter what this number is, right? Because this is positive and this is positive. And so negative minus the positive value is just going to continue to be a bigger and bigger negative number the more that temperature changes. Okay. All right, let's look at the next one. So what if I have a positive delta H and a positive delta S? So I know that my positive delta S is still a favorable condition, but the positive delta H, the endothermic condition, is not favorable. So let's see how those variables play out. So delta G is equal to a positive minus temperature times the positive value. All right, so positive this, S, times the positive temperature value is going to give me a positive number. So we have a positive minus a positive. Well, how do I have a scenario where delta G is negative? For delta G to be negative, this combined value has to be bigger than this positive value, right? So these two things together have to be big enough that when I subtract, I end up with a negative value. So the only way that's going to occur is if this temperature number is big. So when we look at this one, we're going to say that delta G is negative at high temperatures. Okay. I need it to be at high temperatures so that this term is large. So let's write that down as well. The magnitude of the T delta S term, which we're going to subtract, has to be large enough to overcome the positive delta H value for delta G to be negative. Okay. So I need my temperature to be high so that when it multiplies by my favorable positive delta S, it overcomes the unfavorable endothermic positive delta H. Okay. All right, so let's look at our next scenario. All right, we have a negative delta H and a negative delta S. So I know that my negative delta H, that is my favorable condition of H. And I know that my negative S is my unfavorable condition. So let's look at how those variables play out. So delta G equal to a negative minus temperature times the negative value. All right, so the negative value here times the positive Kelvin temperature is going to give me a negative number. So now I have a negative minus a negative, right? So negative minus minus. So that means that this is going to end up being added, right? And so when this gets added, I need it to be low enough that it doesn't overwhelm this so that delta G can continue to be negative or stay negative. So I need this to be small, which means that delta G is only going to be negative when we're at low temperatures. So therefore, delta G is negative at low temps. So we got to kind of negate the effect of that less favorable delta S. All right, so let's write something down for that. The magnitude of the T delta S term has to be smaller than the negative delta H to keep delta G negative and thus favorable. All right. And then let's look at our last scenario, a positive delta H and a negative delta S. So the positive delta H is my unfavorable endothermic condition. My negative delta S is my decrease in disorder, so my more organized, less chaotic state. Neither of these are favorable conditions. And because neither of them are favorable conditions, there's no way, there's no temperature at which delta G is going to be negative here. And so let's look at our signs just to drive home that point. So I have the negative S value. I have the positive temperature, so that's going to multiply, give me a negative number. And so then a positive minus a minus is really just two positive values being added. So delta G is positive at all temperatures because neither of these conditions are favorable. Okay, so those are our four potential interactions of the various H's and S. And so the easiest way to look at it is, right, the two favorable conditions will always make a favorable condition. Two unfavorable conditions will always make an unfavorable condition. And then when I look at my mix of the two, right, the favorable and unfavorable, if the delta S is favorable, I need to favor it. That's a lot of favors, but you know what I'm saying. I need to enhance its position in the equation by having a higher temperature to make the power here of the favorable S greater than the unfavorable H. And then if I have the favorable H but the unfavorable S, I need to reduce the power of that unfavorable S by having a low temperature. All right, so we're going to look at two examples of using Gibbs in this way where I don't have numbers, more qualitatively. We're going to go through two, like, I don't want to call them essays, short answer questions, where we're going to use these relationships. And then we'll look at how to do Gibbs numerically, which is just a buffet of plug and chug. All right. All right, so to understand really what's going on with Gibbs, we need to talk about how the temperature change affects things, because that's always what these questions want to ask is, well, I know what it is now, but what if I change the temperature? And it's always the changing of the temperature that gets to the crux of this. And anytime we're changing temperature, it's all about the magnitude of the T delta S term because the temperature directly affects S. It indirectly affects everything else, but it directly affects the S. All right, so let's look at our first example here. You have an equation, so 2H2S gas plus SO2 gas yields 3S solid plus 2H2O gas. And then you're given a little sentence. At 298 Kelvin, the standard enthalpy change for the reaction is negative 145 kilojoules. All right, so before we even get to the questions, we need to diagnose what's happening up here. And a lot of times, if you can just diagnose what's happening in the equation and in the little blurb that goes with it, you end up answering the questions that come after it before you've even read them. So let's deal with the blurb first. At 298 Kelvin, the standard enthalpy change is, enthalpy is that H or S? Enthalpy is H. So this is my H, my delta H, it's the enthalpy change. And my enthalpy change is negative 145 kilojoules. Well, it's negative, so what do I know? Well, if it's negative, it's exothermic. So that's a favorable condition. Okay, that's good news. And then I also have a balanced equation. So if I was given H, I'm probably going to have to infer S from this equation. So let's see if we can infer what's going on here. I've got, 2 moles of gas combining with another mole of gas. So I've got 3 moles of reacting gas on the reactant side. And what am I making? I'm making 3 moles of a solid, and I'm making 2 moles of a gas. So I'm going from a scenario where I have all gas to a scenario where I have a solid and a gas. Well, if this was all gas over here, then we'd have to look at moles, the difference of moles left and right. But because I've got this solid, I can't look at moles. I need to look at the state of matter. So gas and gas are very disorganized, disordered, diffuse states of matter. Solid is very condensed. So because I'm making a solid out of 2 gases, really even doesn't matter that there's another gas over here. I have a solid. My delta S is going to be negative because this is definitely becoming more organized. All right, so now we've kind of diagnosed everything we can diagnose just from looking at the balanced equation and the little question blurb. So let's look at what our questions actually say. Predict the sign of delta S and explain. Cool, we already did that. So we just need to write down our thoughts about what's happening here in a nice organized sentence. So the first thing I want to do is I want to answer the sign of delta S part of the question. All right, so we already said it's negative. So I'm going to just come out and say delta S is negative, period. Now that's the explain part comes in. So what happens? The reaction is going from a very spread out state to a condensed state. So I'm just going to describe that. The reaction proceeds to a more condensed state as, let's see, we got 3 moles of gas total combine to make a solid and what else? Oh, 2 moles of gas. Okay. And again, it's really that solid that's driving this reaction here. All right, so A, I feel confident about A. Let's look at B. At 298 Kelvin, the reaction is spontaneous. What would happen to the sign of delta G as temperature increases? All right, well, I know that H is negative and I know that S is negative, but you have to be like really observant. What did they just tell me in the question? They said the reaction at 298 is spontaneous. So they told me that at this temperature, delta G is negative. So what I need to know is, as I increase the temperature, is it going to stay negative? Is it going to become more negative? Is it going to become less negative? Maybe turn to 0 and then go to the other side and become positive? So I need to think about how these two variables relate, specifically this S with an increase of temperature. All right, so let's write out our equation with our signs and see if that helps us. Delta G is equal to delta H minus T delta S. So I know that G is negative. I know that H is negative. I know that temperature is a positive Kelvin value, 298, and I know that S is negative. All right, so looking at this right now, I've got this negative value and a positive temperature. When I multiply those, I get a negative value. So a negative minus another negative is adding. So as this gets bigger, it's going to affect this guy, which affects this, right? So how is it affecting it? Right now, a negative minus a negative is a positive. So I'm essentially adding to this minus every time. So as this gets bigger, it's going to start to chip away at this negative value, which then will make this become less negative. So I just need to write that in a sentence, right? As the temperature increases, the magnitude of the T delta S term, right? Because that's the one that's directly affected by temperature. The T delta S increases. And would overwhelm the negative delta H value, causing delta G to become less negative, right? I don't want to jump to directly into it's going to be positive because we don't know how much they're increasing the temperature by. But at the very least, it's going to become somewhat less negative. Eventually, 0, right? Because you can't just jump from negative to positive. You got to go to 0. Eventually 0, then positive. Okay, so as the temperature increases, the magnitude of the T delta S term increases and would overwhelm the negative delta H value, causing delta G to become less negative, eventually 0, then positive. Okay, so that was our first example. We're going to look at one more of these more conceptual things, and then we will do a calculation question with Gibbs. So let me turn my page so we can look at the next one. All right, so this one has 3 parts. So let's look at our equation. We've got 2 KCl solid plus 3 O2 gas, and then, oh, what in the world is happening here? So this is the symbol for a reversible reaction, which we haven't gotten to yet because our equilibrium unit hasn't happened yet. So let me just briefly explain what's going on here. This is a reaction that it is possible for my reactants to become products and my products to become reactants. And so you can address this in what we say is the forward direction, which is your traditional left to right direction, or the reverse direction. All right. So you just need to know that this is forward, going towards what we would normally consider products, and reverse, going towards what we would normally consider reactants. All right, so let's go back again. 2 KClO solid plus 3 O2 gas gives me, in the forward direction, 2 KClO3 solid. All right, so I don't have a blurb like I had in the last one. I just have this equation. So the only thing I can interpret initially is what's going on with S. So let's see what's going on with S. I have a solid and a gas combining to make one solid. So it seems like it's getting more organized. So I'm going to say that delta S is probably going to be negative. All right, and that's all I can interpret. They didn't give me any other information yet. So let's dive into our questions. Predict the sign of the entropy change. Oh, good. The one thing I could answer. As the reaction proceeds to the right. So in the traditional direction, that's what they want to know about. And that's the one that I already said. So good. So we know entropy is delta S. We already said delta S is negative. So let's just write a sentence about that. Delta S is negative. All right. Why? The reaction proceeds to a more condensed state as 2 moles of solid and 3 moles of gas combine to make 2 moles of a solid. All right. Part B. If the reaction spontaneously proceeds to the right, predict the sign of the enthalpy change and justify. So what did they just tell me? What is this hint that they gave me? Oh, they told me that I've got a negative delta G. Okay. So I know that this overall has to be favorable because delta G is negative. And I know that my S is the unfavorable condition. So how can I make this favorable when I have the unfavorable S? Well, what is it asking me? It wants me to tell the enthalpy. It wants me to tell the H. Well, if the overall G is negative and favorable, and my S is unfavorable, then doesn't my H have to be favorable to make this happen? The only way that this can happen. So let's look at our equation. So delta G equals delta H minus T delta S. I know this is negative, right? This is the one I don't know. I know that my temperature is a Kelvin positive value, and I know that this is negative, right? So the negative here times the positive temperature is negative. So if this is being now added, because negative and negative is positive, right? This has to be negative in order for this to be negative. So we're just going to have to write a nice little sentence about it. I need to acknowledge they gave me this information, though, because that's the only way I figured it out. So as stated, the reaction is spontaneous. Therefore, delta G is negative. Okay. Given a negative delta S, the enthalpy, or you could have just said the delta H, must also be negative. Okay. And what we wrote up here kind of really is our justification, our explanation for this. All right. C. The direction in which the reaction spontaneously proceeds changes as the temperature increases. Explain. All right, so this goes back to this being a reversible reaction. So in question B, or question statement B, they said the reaction spontaneously proceeds to the right. So if going to the right, delta G is negative, doesn't it make sense that going to the left at that point, delta G would be positive? Because if the forward reaction is spontaneous, wouldn't the reverse be the opposite, less so? So the direction in which the reaction spontaneously proceeds changes when temperature increases. So if the forward reaction becomes not spontaneous, isn't it the reverse reaction became that way? So let's look at what's increasing the temperature does. Who does that affect? It affects our negative delta S. So delta G equals, let me slide this up just a little bit, delta H minus T delta S. If I know that this is negative temperature and I know that this is negative, right? The bigger this gets, right, it's going to be added. Isn't it going to overwhelm that and make this go from being negative to being 0 to being positive? And once it becomes positive, then that forward reaction is no longer spontaneous. If the forward reaction is no longer spontaneous, now the reverse reaction is spontaneous. So it's because, again, the magnitude of the T delta S term has gotten so big, it's overwhelmed this negative delta H. So as the temperature increases, the magnitude of the T delta S term, which is subtracted, increases, therefore becoming large enough to overcome the negative delta H, causing delta G to become less negative, 0, then positive, as temperature goes up. All right. So again, if the magnitude of the T delta S term is what is causing this. All right, so that's 2 examples, and they all come in different shapes and sizes, but what you're going to see as you do these, you're going to have to look at your equation, infer S, then they're either going to give you H or give you G so you can figure out H, and then you're going to be asked what's going to happen as I change the temperature, which is always about what happens to S. They're very formulaic. So you're just make sure you're watching out for those key things. All right, so the last thing we're going to do with Gibbs is look at Gibbs with the calculations. So how to numerically determine Gibbs, which is pretty darn easy if you ask me. All right, so Gibbs with calculations. Our equation, which we've just used over and over again, is delta G equals delta H minus T delta S. So you're going to determine your variables, and it's a buffet of plug and chug, right? Just going to make sure that you're plugging and chugging the right things. So here's my equation. At 25 degrees Celsius, delta H was found to be negative 198 kilojoules per mole. Delta S was found to be negative 187 joules per mole Kelvin. Calculate delta G and state whether the reaction is favorable. All right, so I've got to plug and chug, right? Well, before you plug and chug, you got to watch out. Look at your units. Delta H is in kilojoules. Delta S is in joules. Delta G is going to want to be in kilojoules. So I need to make the S into kilojoules that's currently in joules, right? Remember that 1 kilojoule is equal to 1,000 joules. So I need to divide this by 1,000. And remember that my temperature has to be in Kelvin. And to get to Kelvin, I take my Celsius temperature plus 273. So I got to take my 25 and make it into Kelvin. So 25 plus 273 is going to make this 298. Okay. And then now I can just plug and chug. Let's do this. Delta G is equal to my delta H, negative 198 minus my temperature, 298 times negative 187 divided by 1,000. And yeah, I could have put the units in there, and I probably should have. But what I want you to notice is that my Kelvin temperature here and the Kelvin on the delta S term is what cancels out, and I'm going to be left in kilojoules per mole. All right. And so let's do our math here. So let's see. Negative 198 minus 298 times negative 187 divided by 1,000. All right. And what do I get? It would be helpful if there wasn't a glare. There you go. Negative 142.274. I'm doing addition and subtraction. So my rule is decimal places. None of my values have a decimal place, so I need a nice whole number. Delta G is equal to negative 142 kilojoules per mole. And so if this value is negative, what do I know? It's favorable. Okay, let's look at number 2. 4 FeS, or Fe solid, plus 3 O2 gas yields 2 Fe2O3 solid. Find and classify delta G, little circle thing. What does that mean again? Oh yeah, remember that means delta G naught. Delta G naught, that naught tells me I'm at standard temperature. Standard temperature is, for this, 25 degrees Celsius. That's what the naught means. So I don't have to give you the temperature if I tell you it's naught. And then I'm given a delta S naught value and a delta H naught value. All right, so I'm going to do the same thing I did up here. I'm going to convert my joules to kilojoules by dividing by 1,000. I'm going to convert my Celsius to Kelvin by adding 273, and then I'm going to plug and chug. All right, so delta G naught is equal to negative 1652 minus 298 times negative 543 divided by 1,000. Okay, and so let's see what I get when I do that. I'm going to hold my calculator out of the way so you don't get that glare this time. Negative 1652 minus 298 times negative 543 divided by 1,000. Okay, and so I get negative 1490.186. No decimal places, so delta G naught is equal to negative 1490 kilojoules per mole. It's negative, so it's favorable. All right,